Okay, now that we've got the droop adjusted on the this integrator, the next step we're going to do is to adjust the common mode rejection ratio. Again, as I said in the intro, any DC voltage here is nulled out because you're integrating in up and then you integrate down. And if you make this resistor match perfectly with this one by trimming this potentiometer, the circuit to first order and really fairly high order becomes insensitive to the DC voltage at this point. The reason you have a DC voltage there is because the whole circuit is AC coupled here. The CCD is off in this direction. And so you actually do have an offset here which is dependent upon the average signal level. In fact, it's about 39% of the average signal level because of a bunch of factors that all come in. And if you don't have this properly adjusted, you are then sensitive to that DC level, and we don't want that. You want to be insensitive to that and only sensitive to the step when you do the charge transfer on the CCD. That is, you don't want it to be sensitive to the history of what the pixels were like, previous pixels were like. You want to only be sensitive to the current pixel. Anyway, so we're going to adjust that, and so we've got our post amplifiers back in the box, and before I turn the box on, we need a signal to simulate, let's say, the DC level. And what I'm going to use for that is a signal at 1 hertz, so a very low frequency signal. It's a triangle wave, though you could in principle use a sine wave if you wanted to. It's got an amplitude of 320 millivolts peak to peak, which matches the expected DC offset as you go from a bias image to a very bright flat field image. And it has an offset of 160 millivolts. So in fact, that gives you a triangle wave. Since this is, the amplitude is in millivolts peak to peak, and you've offset it by half of the peak to peak amplitude, you have a signal which is going from 0 up to plus 320 millivolts and then back down to 0. Okay, so let's turn the noise back on, noise maker back on. And we've got to get the program doing what we want it to do. And the program, I'm still tied to the box here with my strap. There is just a huge number of commands in the program, but I think if you just bring it up and do a ZA, which will automatically zero the signal on the display, and you see now the signal is near 0, believe it or not there. And then you need to get a scale that gives you good sensitivity. So I'm going to do scale, and all the commands are a command and a return, and then it may ask for values. In fact, it says the old scale were 2020, and what I want now is 2,2. And if you look back over at the screen, I don't know whether you can, we're getting the screen on the video? Good, excellent. So what we're looking at now is a nice flat field. We're only reading out a couple hundred lines, and we're binning a lot, so we're just exercising the post amplifiers. We're not taking any data. There's no CCD here. Get off the cord. And what you see is a little bit of noise, and there's a little bit of offset there. And I think, in fact, I'm going to CZA and 50 just to make that a little brighter. And I'm going to go do a ZA again. I just changed the level that it was the default level that was coming to the screen to make it a little brighter, a little easier to see.
What was the command that made it brighter?
CZA, Charles Zebra Alpha, then it requires a value, and I put in 50 as the value there. So that's a little better than the default in the program. And after you do that, you have to do ZA, Zebra Alpha, again to do the automatic zeroing. Okay, so then the trick is how you get the signal into the post amplifiers, and I have them actually coming out on this handy dandy micro gripper with a piece of gold-plated brass wire that I cut off a connector.
And that's the output of the signal generator.
It's the output of the signal generator, exactly. So again, you need to connect up your ground, and you can use the same place that you were using before for the ground. Don't yank on the resistors, you know, just go nice there. And it works out quite nicely that you can put the signal into two channels at the same time. So in fact, I'm injecting the signal here just after the coupling capacitor, and I'm injecting that signal into channels 4 and 8. Believe it or not, you can see that once you get the feel for what this chart means in terms of the post amplifiers, you'll love that. It'll be huge. And if we look at what we've got here on the screen, we don't have our nice flat field anymore at all. We've got this, on channel 8 especially, we've got this signal going up and down and up and down at 1 hertz, because it's the 1 hertz signal that we're injecting and it's not being rejected. That is, the common mode rejection ratio on channel 8 is terrible. Okay. I don't know what I said before, but in fact we're injecting signals into channels 8 and 4. Is that what I said before? I should have said that. So let's try to fix 8 first. There's the pot for channel 8, and those are the 8 pots for the 8 channels in the common mode rejection ratio. And as I turn the pot, I can get it so that the signal goes up and down almost not at all. And if I turn it too far, then I get it going with the opposite phase. So here we are watching the signal, and we got this up and down now, and if I turn the pot, in this case clockwise, I can get to a point where it's hardly moving at all. And in fact, what you get to is a point where all the second order effects are more important, and you'll see it actually jumping at twice the frequency, moving very slightly at twice the frequency. And that's about the best you can do. I've lost my pot now. Excuse I'm blocking the camera. So again, if you go in one direction, you'll get signals that are in phase with the driving signal, and if you go in the other direction too far, you'll get signals that are out of phase with it. And if you go in just the right place in the middle, you get rid of all the first order stuff, and you get this little jumpy at twice the frequency. Now the other channel that we're driving right now is 4, and I don't know where 4 has been, but it's pretty well adjusted, so we're going to leave it alone. We can only make that worse. Then I can move my signal source down to...
Come around and see if I get a shot of where
Yeah, you really need that. So again...
So we're injecting which channels in there now?
Well, we were up here going through both boards. That was 8 and 4. You look up here on the chart and see that this... you're driving the card that has the preamps for channels 4 and 2 and 8 and 6. Those are these 2 cards. And we were in the upper one of these 2 possible input signals. That is, not using that coupling capacitor instead of not using that coupling capacitor. So we did 8 and 4, and now we'll go down to this, and that is 6 and 2. And sure enough, if we look over at the screen, both 6 and 2 are pretty bad. Let's fix 2 first, which is the bottom pot of this guy. And I don't know which way you have to go, but oh, I guessed right, huh? There we are with it wiggling at about 2 hertz, a little bit of 2 hertz still in there, not much 1 hertz. And then I'm going to go over to the other pot on channel 6. Getting better, better. Less bad, less bad, less bad. And that's about as good as you can get. If you notice, these two channels that we're driving, the signals are quite a bit noisier than channels that are not being driven, and that's just because you're hooking up with this from a signal generator, which is not perfect and has a lot of noise in band, in the band for the CCD signal. Okay, that's 4 of them done. We can go around on the other side now.